Previously, we did a video on the math behind Principal Component Analysis, PCA. In this video, we will show how to use PCA as feature engineering for machine learning. We shall show that PCA can improve the model performance with decorrelated features and fewer parameters. First, we will import all the necessary libraries and read in the data. If we look at all the columns of the data, there are 31 columns, V1 to V28 time, amount, and class. And if we plot the distribution of the class, we can see that it is highly imbalanced with very few non-fraud cases, and there are some cases of fraud. Next, we will do some data pre-processing. We will first remove the time and amount columns since we do not think they will contribute to the model prediction. Then we will remove the missing data and check that there is no more missing data. And we will reduce the number of data to 2000 in order to speed up our model training. Next, we will do a min-max scaling and split the data into training and testing data set. And then we can now do a logistic regression and fit into the training data and then do a prediction on the testing data. We will look at the performance metrics from the classification report. If we look at the fraud case, we get a precision of 0.6 and the record of 0.5 and the F1 score of 0.55. And if we look at the confusion metrics, we do see that there are a significant numbers of misclassification, 8 over here and 12 over here. The accuracy of the logistic regression is very good, almost perfect, but the AUC score, we get a modulus of 0.75. Now, let's look at how PCA can improve the model performance. For PCA, we need to do a standards normalization, as one of the underlying assumptions of PCA is that the data is Gaussian distributed. So we perform a standard normalization on the original data, and then we do a PCA on all the features, the 28 features, and we take a look at the cumulated explained variance. We see that we can reduce the number of features by taking less features. For example, 10 that will account to about 60% of the information of the data. And if we look at the individual contribution of the components, the first component account for the most information, about 13%, followed by the second, about 8%. So let's do a PCA for only 10 features, and that will reduce the features from 28 to 10, and then we fit to the data after the standard scaling. And let's look at the explained variance for all the 10 data. And if we look at the shape of the data after the PCA, we're left with 10 features. And that's how the data look like. If we plot the first component versus the second component, we can see there are some classification. So one class is on the left and the other class is on the right, although the clustering is not perfect. Next, we are going to do a logistic regression. Before that, we have to split the data on the data that is after the PCA. And then we perform a logistic regression on the training data after the PCA and the prediction of the testing data also after the PCA. If we look at the classification report, and now we see that the precision has improved from the previous 0.6 to 0.73 and the recall from 0.5 to 0.67, and the F1 score has also improved to 0.7. Let's look at the previous result, 0.6, 0.5, 0.55, and now we are getting 0.73, 0.67 and 0.7. If we look at the confusion matrix, we see that the number of misclassification has reduced significantly. The accuracy, we are getting almost close to 1, but the ROC and AUC score we have improved from 0.78 to 0.83, right? Let's look at the previous data, 0.75, and now we are getting 0.83. This shows that PCA can improve the model performance, and the reason is because we have less features and all the features are all non-correlated. This concludes the video tutorial on PCA for machine learning. The code can be downloaded below. If you'd like to feedback on this video tutorial, we welcome your comments below. If you like the video, please share and subscribe to our channel. Thank you.